Hello everyone, I'm Nhung, the final year student at Hanoi University of Science and Technology, also the corresponding author of the paper named Wireless Wearable Electromyography Acquisition System, utilizing reduced graphene oxide-based sensor. On behalf of my co-authors, I would like to present to you our research. This is the brief of my presentation today, which consists of 5 main parts. First and foremost, I would like to explain you our motivation for choosing this topic. Nowadays, the demand of wearable biomedical device for health monitoring increased incredibly due to its low cost, feasibility, convenience, and it can reduce hospital visits for patients, which is really necessary in COVID-19 pandemic. So, many wearable devices for health monitoring have been developed. For example, smart belt, smart shoes, or smart shirts. Those devices record various biomedical signals such as electromyography, electrocardiography, and electroencephalogram to analyze and give us useful information about our health. Among many different biomedical signals, electromyography or EMG signal is myoelectric signal that is formed by physiological variations and expressed through the muscle fiber membranes. We realize that EMG signal has a lot of applications in our life. For example, it can evaluate prosthetic applications. It is also used in recovering program for musculoskeletal disorders, and also it can help us to monitor muscle in sport training or sport practicing. To acquire EMG signal, some different types of sensor can be used. For instance, silver chloride is disposable and wet sensor. It uses wet gel to stick the sensor to human skin to take signal from our body. However, because of the wet gel sticking to our skin, it can cause discomfort for continuous monitoring applications. Another type is dry sensor, like metal sensor. However, this type of sensor is really rigid and still cause inconvenience for users. Therefore, recently, textile-based sensor draw more attention for certain advantages comparing to silver chloride or metal ones. Textile sensor is not require gel to stick to the skin like silver chloride sensor, and also not rigid like metal sensors. Moreover, it can be incorporated to clothes and reusable. So it is considered as the most suitable sensor for wearable applications. There are also some research confirmed that physiological signal taken using textile-based sensor is compatible with their commercial sensors like silver chloride. So we decided to design a system to monitor and analyze EMG signals using textile-based sensor. The figure 1 is the diagram of our system, which consists of graphene-based EMG electrodes, analog acquisition circuit with wireless communication module, and an Android application. To acquire EMG signal from a certain muscle, two EMG electrodes are placed on the muscle to take differential EMG signal, and the third one is used as a reference electrode. An EMG electrode has a structure like we described in figure 2. It is composed of one graphene-based textile sensor and a metal male button. They are attached to each other by silver epoxy to reduce contact resistance. EMG electrodes are sold to close to monitor real-time EMG signal. The differential EMC signals are amplified, filtered, and then digitized before being transmitted to the smartphone through Bluetooth connection. And then it is processed, stored, and displayed on the smartphone. Now we wanna explain the way we manufacture graphene sensor. The graphene-based sensor is created by deep coating nylon and polyester fabrics using thermally reduced graphene oxide technique. Nylon fabric was selected to provide a chemically stable and smooth substrate surface while being highly flexible and stretchable. On the other hand, the polyester fabric can provide excellent flexibility along with good heat conductivity and electrical insulation. Figure 4 is the block diagram of our proposed acquisition circuit. Two EMC electrodes named mid and end placed in the middle and at the end of the muzzle respectively provide differential input signals to the analog circuit. To ensure that the low EMC input signal can be drawn to the acquisition circuit, two buffers are employed according to two input paths to produce high input impedance. The differential input signal is then amplified by a low noise and high common mode rejection ratio instrument amplifier to remove all mismatches introduced from two EMC electrodes. As we study, the most useful and important frequency range of EMC signal is from 50 Hz to 150 Hz. So low pass and high pass filter are adopted to remove all unnecessary signals. The schematic of analog acquisition circuit is shown in figure 5. The main duty of high-pass filter is to cancel DC offset caused by potential mismatches from instrument amplifier and by the low-pass filter also. Besides, the low-frequency artifact noise introduced by the EMG electrodes displacement during measurement can be mitigated by high-pass filter as well. In this paper, a servo feedback-based active high-pass filter is employed to avoid using large capacitor connected in series in main signal paths, as in a conventional passive high-pass filter. The servo feedback is an inverting integrator that is connected in feedback loop between the output of instrument amplifier and its reference input pin. Its cutoff frequency is set at 50 Hz. The high-pass filter is followed by a first-order low-pass filter with cutoff frequency of 500 Hz that worked as an anti-aliasing filter. And the analog EMG signal, after being amplified and filtered by analog circuit, is then converted into digital signal by a 12-bit analog digital converter, pre-integrated in Bluetooth Low Energy module. The reason why we choose Bluetooth Low Energy module is because it can minimize power consumption in wireless data transmission. And finally, the EMC signal is transferred to an Android application. Here in figure 6 and figure 7 is the interface of the Android application that we designed. This app can visualize real-time EMC signal like shown in figure 6. It also can save data and user information to internal storage and database. After saving data, the data can be analyzed in using fast Fourier transformation to display frequency domain in different units. And important parameters also are calculated, like minimum or maximum amplitude, or mean frequency and median frequency for muscular fatigue monitoring. To evaluate the proposed acquisition system, we set up some experiments, like in figure 8 is the experiment protocol. Figure 8a shows the EMG acquisition circuit, which includes a circular main board connected to an SD card port by a flexible cable. 3 EMG electrodes are sold into a handmade armband. This armband is designed to wrap tightly around the subject's arm. A thin and elastic fabric layer is used to cover outside of the setup to keep the whole system stable when the subject performs physical activities. The EMG signal from graphene sensor is compared to commercial sensor silver chloride. So we carried out experiments on biceps muscle. The subject is required to sit comfortably and steadily, then put the arm into the air and flex the arm like figure 8b every 5 seconds, with a 4 seconds relaxation like figure 8c between each flexation. The experiment is repeated with graphene sensor based on 2 different types of fabric, nylon and polyester, and also silver chloride sensor using our design circuit. For the experiments with calf muscle, the tester is asked to do toe stands for 1 second, then back to normal standing for 5 seconds to ensure a full relaxation of muscle. During the test, two separate electronic circuits are used to pick up the signals from 2 legs. A knee band is designed to wrap each leg to keep our sensor in constant contact with the skin. The knee band electrodes and the acquisition circuit are set up similarly to the experiment on biceps muscle, like described in figure 9a and b. Finally, after all experiments, we come to the result. Figure 10 shows the EMG signal measured from biceps muscle by silver chloride and different types of graphene fabric. The recording is shown in time domain like figure 10a. Each active contraction burst of EMG signal corresponds to the moment when the tester flexes the arm. During relaxation, there is no signal and only an EMG baseline is observed. It can be seen that the amplitude of EMG signal acquired by graphene sensor is higher than that of silver chloride sensor. In addition, the fast Fourier transformation is applied to compare the magnitude frequency domain, and its result shown in figure 10b. We can realize that the major power spectrum lies in the frequency range of 50 to 150 Hz. Within this range, the signal obtained from the graphene sensor shows higher amplitude than that of silver chloride sensor. In table 1, we calculate some parameters for comparison between silver chloride and graphene sensor, such as average amplitude, SNR, signal noise ratio, and cross correlation. Graphene sensor offers a high SNR of 24 dB comparing to only 17 dB achieved by silver chloride. So it confirms that the graphene-based sensor offer better performance. For experiments on calf muscle, The EMG signals obtained from two legs by graphene sensor are shown in figure 11. Although EMG signal from both legs show similar shape, the signal amplitude of right leg muscle is slightly higher than that of the left leg. In order to quantify the comparison between EMG signal from left leg and right leg, root mean square operation is performed to smooth the signal and still reflect the mean power. The result is shown in figure 12. It's obvious that EMG signal collected from the right leg is stronger than that of left leg in nearly all pools. So this could be explained by the fact that the subject is right-footed. In conclusion, in this paper, a novel, easy-to-use system intended for flexible and wearable monitoring EMG signal by using graphene sensor has been presented. The obtained signals from biceps and calf muscles are evaluated. A better performance is observed for graphene-based textile sensor in comparison with the commercial sensor. The experiments analysis shows that the reusable RGO-coated fabric is a promising alternative to commercial sensor in muscular activity monitoring applications. And finally, that is all the reference that we used in our research. Thank you for listening, and if you have any question, please feel free to ask us.